Rigid Body Dynamics, Lecture 2. In the last lecture, we have learned about rotating bodies. We have learned about rigid bodies, some of the characteristics of rigid bodies such as center of mass, moment of inertia, etc. In today's lecture, we will learn about rotating bodies. In this video, we will learn about rotating of bodies through different axes. Then we will also learn about theorems of moment of inertia such as parallel axis theorem and perpendicular axis theorem and their proofs. Axis of rotation. A body which rotates is about an axis. The axis of rotation specifies the moment of inertia of that body. A rotating body always rotates about an axis, and that axis is called axis of rotation. Axis of rotation can be through the center of the body, can be at the sides of the body, or anywhere or outside the body. An axis which is through the center of the mass of the body creates least a moment of inertia. As we have discussed in the last lecture, moment of inertia is the resistance, is a kind of resistance which the body, any rigid body exhibit when it is about to be rotated. It is called rotational inertia. So the inertia or the resistance to rotate will be very less when the axis of rotation is passing through the center of mass of the body. But in case if the axis of rotation is not through the center of mass of the body and through any other part of the body, maybe through the sides of the body or maybe outside the body, then the moment of inertia will be greater. Moment of inertia increases as the axis of rotation moves away from the center of mass. Here in this picture, the moment of inertia is very less when the body rotates about the red axis, and it will be greater when the body rotates about the blue axis. When the body, if it is rotating about some other axis, maybe this green axis, then the red axis will offer less moment of inertia, the green axis will offer even more moment of inertia, and the blue axis will offer the greatest moment of inertia. So the moment of inertia of a body purely depends upon the mass of the body and the axis of rotation. First theorem on moment of inertia is parallel axis theorem. In parallel axis theorem, we say that the moment of inertia of a body about any axis I will be equal to moment of inertia of the same body about an axis passing through its center of mass plus mass of the body multiplied by the distance between the axis of rotation and axis through the center of mass. That is, when we have a body rotating about here and we have here the axis of rotation which is passing through the center of mass, and the body is rotating about some other axis passing through somewhere here, then the moment of inertia will be the sum of moment of inertia of a body when it rotates about the center of mass plus the mass of the whole body and the distance between these two axes. I is equal to ICM plus MA squared, where M is the mass of the body, ICM is moment of inertia when the body rotates about its center of mass, and A is the distance between the axis of rotation and axis through the center of mass. Let us try to prove the parallel axis theorem. Consider the body is rotating about the axis r, which is at a distance a from an imaginary axis which is passing through the center of mass. Consider a small mass element dm at a distance r from the center of mass. Then the moment of inertia of the small mass element dm about the axis r will be di, which is equal to dm into a plus r the whole squared. We know the moment of inertia, equation of moment of inertia is mass into distance square. That is mass into the distance between the mass and the axis of rotation squared. Here the mass of the mass element is dm, therefore dm into, and the distance from the mass element to the axis of rotation r is a plus r. Therefore the total distance is a plus r. So we can write it as dm into a plus r the whole squared. Now, the mass of the entire body can be calculated by summing up all the mass elements, considering all the mass elements throughout the body. In this case, I will be the summation of this term, which is dm into a plus r the whole squared. Here, a plus r the whole squared can be split into a square plus 2ar plus r squared. Now, sigma dm into a squared is can be written as sigma dm as the total mass, therefore the total mass is m. We can write sigma dm into a squared as ma squared. Similarly, sigma dm into r squared can be written as mr squared, while 2 into sigma dm into ar. In this case, you need to understand that r is any distance. R is the distance to this mass element. Similarly, you can find a mass element which is diagonally opposite, which is just opposite to this mass element at a distance negative r. So these two mass elements will cancel each other. You can find a mass element here which is at a distance negative r from the center of mass. So these two terms cancels each other. Similarly, you can find n number of masses which is at diagonally opposite positions, and these mass elements, terms of these mass elements will also cancel each other, as their distance from the center of mass will be either positive r or negative r. So we can cut off this term, and this term will goes to 0. And the answer will be I is equal to ICM plus MA squared. Here ICM is the moment of inertia about the center of mass. Here you can see that the dm mass element, the moment of inertia of this mass element about the axis through the center of mass is the mass into r squared. On summing up, it will become capital M into r squared, which denotes the moment of inertia about the center of axis. Therefore, mr squared can be written as the moment of inertia through the center of axis, and the ma squared is here, where a is the distance between this axis of rotation and the axis through the center of mass. In this case, you need to remember that there is no such axis through the center of mass. We are just imagining that we have an axis here. If the body was rotated about the center of mass and not about the R, then the moment of inertia will be ICM. In this case, the body is rotated about R and not the center of mass. Therefore, since the axis is away from the center of mass, the moment of inertia or the rotational inertia, that is the resistance offered by the body to rotate, will be higher. Therefore, we have a plus term here. Therefore, the total moment of inertia I will be equal to the moment of inertia about the center of mass plus the mass of the body into the square of the distance between the center of mass and the axis of rotation. Hope you are clear with the derivation. In the derivation, first we have considered a small mass element dm and we have calculated its moment of inertia about the axis r by considering the mass into the total distance squared. And the total distance here is a plus r the whole squared. Therefore, to find the total moment of inertia of the complete body, we need to consider every mass element over here dm and we will sum up all those moment of inertias. Therefore, we have summed up all those moment of inertias here and we have opened this square as a square plus 2ar plus r squared. And the sum of the mass into a squared can be written as the total mass into a squared. The sum of the mass into r squared can be written as total mass into r squared. But here we doesn't have a square term. So the negative values will appear as negative terms. Therefore, the positive values will cancel with the negative values and this term goes to 0. The reason why this term and this term doesn't go to 0 is that we have a square term here. Even if we consider a particle which is at the position -1, the -1 squared will give you 1 only. Therefore, the negative position, the dm's at the negative positions will also add up and will not cancel each other. But in this case, since we doesn't have a square term here, the negative r will appear as negative r only and it will cancel with the positive r's. Therefore, this term will cancel out. And in the next line, at the end of the equation is the total moment of inertia equal to moment of inertia about the center of mass, and that is the mass into distance to the center of mass, that is r squared, plus the mass into square of the distance between the center of mass and the axis of rotation. Hope you are clear with this. Now we will move on to another case. In this case, let us consider the mass element which is somewhat displaced, not in parallel to the center of mass and the axis of rotation. Now the distance towards the center of mass is r and the distance towards the axis of rotation is x. Now what we need to find is the mass and rotational inertia about r. The rotational inertia about r will be equal to dm into x squared. But we need to find what is x squared. Therefore, also we need to find the value of r squared. Therefore, in case we will drop two perpendiculars here with the lengths b and h, where h is the vertical perpendicular length and the b is the horizontal length here. Therefore, the moment of inertia about the axis r now is the dm into this distance x squared. Here in this case you can see here a perpendicular, a 90-degree angle here. So this is a right angled triangle with hypotenuse is equal to h and the base is equal to a plus b and the height is equal to h. This is the triangle, the right angled triangle. So according to Pythagoras theorem, we know that the hypotenuse square is equal to the base square plus altitude square. Therefore, the x squared will be equal to a plus b the whole squared. This is the base. A plus b is the length of the base. Therefore, a plus b the whole square plus h squared. Therefore, the moment of inertia about the entire body will be the sum of this term, that is dm into x squared. Let us substitute for x and open this bracket as a square plus 2ab plus b squared, and the h squared will follow as such. Now, sigma dm into a squared will be equal to m into a squared. As we doesn't have any negative terms here, sigma dm is the sum of the all mass elements all over the body, and that will be equal to total mass of that body itself. Therefore, sigma dm will be equal to m. Therefore, sigma dm into a square will be equal to m a squared. Similarly, sigma dm into b squared will be equal to m b squared. Sigma dm into h square will be equal to m h squared. But in the case of sigma dm into ab, we can find that these terms are not square terms, so that there can be a possibility of finding another term which is equal to minus 2ab, and these terms will cancel each other when we consider the entire body. Therefore, this term here can be cancelled out, and the term which remains are only the terms, that is a squared and b square plus a square. So we can cut off this term, and the terms which remains are a squared and b square plus h square. Here again look into the diagram and you can see another right angled triangle with r as the hypotenuse and h as the altitude and b as the base. Again, according to Pythagoras theorem, we know that the hypotenuse square, that is r squared, is equal to the base squared, b squared plus altitude square, h square. Therefore, r square is equal to b square plus h square. So we can substitute b square plus h square in this term with r squared. Therefore, sigma dm into b square plus h square will become, sigma dm will become m, and the b square plus h square will give you r squared. Therefore, this term here, it will cancel out. This term will cancel out. This term will go to 0 as we have no square terms here, and the terms which will exist is only mr squared and ma square. Here r square was substituted from b square plus h square from the right angled triangle, and also using the Pythagoras theorem. So now listen what we have here. We have here is a mass into distance between the axes, that is a, and the mass and the distance of that mass element towards the center of mass. Therefore, the total moment of inertia of that body will be equal to moment of inertia about the center of mass, and that is equal to mr squared. And the moment of inertia, that is the mass of the body multiplied by the distance squared. In the last case, in the previous case, we had the mass element right here, which is parallel to the axis. Therefore, there was no need to consider another possibilities. So in this case, we have taken a general case. So we have some more steps, but it is simple, I gather. I will repeat the whole process again. We have a mass element dm here. So the moment of inertia of this mass element about the axis r will be dm into x squared. But we doesn't have the term x squared, so we need to find what is x squared. So what we have done is we have dropped a perpendicular here and here, and we considered this right angle to triangle and wrote x square will be equal to a plus b the whole square, that is base square, plus the altitude square, that is h square. Therefore, this is the moment of inertia for this small mass element dm. What we need to consider is the moment of inertia for the entire body. So we need to consider a mass element here, 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 and throughout the body. Therefore, we can sum all these dm's here to find the moment of inertia of this complete body. Therefore, moment of inertia of the entire body about an axis r will be equal to sum over this term, that is dm into x squared. But we already know that x squared is a plus b the whole square plus h squared, and we know how to open the bracket as a square plus 2ab plus b squared. So here we have opened the bracket, and inside the bracket we have seen that we have 3 square terms, and that will remain a constant even if we have a negative value. That is negative 2 squared will be a plus 4, and negative 1 squared will be a plus 1. So these terms won't cancel each other. But in this case, since we doesn't have a square term here, a negative a will result in minus 2ab, or a negative b value will result in minus 2ab. Negative a will be an a somewhere over here. A b can be somewhere over here. So when we consider other mass elements, the mass elements which are diagonally opposite to the considering mass elements will cancel each other. So this term will go to 0, and only a squared, b squared, and h squared multiplied by sigma dm will exist. Now we know that sigma dm a squared will be equal to the total mass of the body m into a squared. Again, sigma dm into b squared will be equal to total mass of the body m into b squared, and sigma dm into h squared will be equal to mh squared. Again, from the diagram, we know that we consider this right angled triangle with r as the length of the hypotenuse, b is the base, and h is the height. Therefore, r squared will be equal to h squared plus b squared. So, we can substitute b square plus h square with r squared, and sigma dm r squared will become mr squared. Now, mr squared is the moment of inertia of any body which is rotating about its center of mass, about an axis passing through its center of mass. So we can write mr squared as ICM as the moment of inertia about the center of mass plus the term ma squared. Therefore, According to parallel axis theorem, if we have an axis parallel to the axis through the center of mass about a distance a, then the moment of inertia through this axis will be equal to moment of inertia experienced by the body when it was rotated about the center of mass plus this product of the entire mass of the body multiplied by the distance between the center axis through the center of mass and the axis of rotation a squared. Therefore, I is equal to ICM plus MA squared. You need to consider that here we have a plus term which denotes that when the moment of inertia is least, when the body is rotated about its center of mass, and when the axis R moves away from this, the distance A also increases. That is, when the axis moves away from this, the moment of inertia or the resistance to rotation offered by the body will also increase. Next theorem is perpendicular axis theorem. Perpendicular axis theorem is used only for laminar bodies. What are laminar bodies? Laminar bodies are bodies which have negligible thickness, just like a paper or a note. We have something which have negligible thickness, just like a leaf or a paper. The bodies which have very small thickness, the bodies which has only dimensions in the x and y directions are called laminar bodies. And perpendicular axis theorem is applied only for laminar bodies. The perpendicular axis theorem says as that IZ, that is moment of inertia of a body when it is rotated about the Z axis. Rotation about the Z axis means rotation of the body in this direction. This is the rotation about the Z axis. The body is rotated about the Z axis. So the body is rotating in this direction, and this is called the moment of inertia, the rotation about the Z axis. That is, therefore, IZ is the moment of inertia experienced by the body or the resistance which is shown by the body when it is rotated about this axis, when it is rotated in this fashion. This will be equal to when the body is rotated about this axis, that is, when the body is going around in this fashion about the y-axis, when the body is going around in this fashion, and that is IY, moment of inertia, resistance offered by the body when it is rotated in this fashion, plus the moment of inertia, the resistance offered by the body when it is rotated about this axis in this fashion. Therefore, the IZ, moment of inertia experienced by the body when it is rotated about the Z axis, will be equal to the moment of inertia of the body about the X axis, that is in this fashion, and about the Y axis when the body is rotated about this axis. Let us prove the perpendicular axis theorem. Again, consider a small mass element dm which is from the center of the body. Drop two perpendiculars towards the axes x and y and mark the length, that is the intercept, the length formed by as x and y. This shows that the r here, r has traveled a distance x and also traveled a distance y to reach this point r. The r has traveled a horizontal distance x and traveled the vertical distance y to reach this point R. Therefore, according to Pythagoras theorem, we have a right angled triangle here. We can have R square is equal to x squared plus y squared. The moment of inertia of this small mass element dm about the z-axis, that is, when the disk is rotating in this fashion, this mass element will go around, and the moment of inertia experienced by this small mass element to rotate about this axis will be equal to the mass into distance to the axis of rotation. Therefore, dm into distance to the axis of rotation. But for the entire body as concerned, as we have a lot of dm's here, we can sum up all their moment of inertia and can write Iz, the moment of inertia of the entire body about the axis z is equal to the sum of all the moment of inertia experienced by many mass elements dm. Therefore, sigma of dm into r squared. But as I have already told you, r squared can be replaced by x squared plus y squared from this diagram using the Pythagoras theorem. Therefore, on replacing r square, we can write Iz is equal to sigma dm into x squared plus y squared. By opening the bracket, we can write sigma dm into x squared plus sigma dm into y squared. Sigma dm is the sum of mass throughout the body, and that will be equal to the total mass of the body. Therefore, this equation will become m into x squared plus m into y squared. We know the fashion mass into distance squared is the moment of inertia. Now here the distances are the distances about the x-axis and the distances about the y-axis. So this will be equal to the mass when the mass is sitting over here and it is going around in this fashion, plus when the mass was sitting over here and it was going around in this fashion, the both action will provide some moment of inertia, and the sum of those moment of inertia is equal to when the mass is sitting over here and going around in this fashion. Therefore, mx squared is equal to Ix, the moment of inertia about the x-axis. My squared is Iy, that is moment of inertia about the y-axis. Therefore, according to perpendicular axis theorem, Iz, that is the moment of inertia over the z-axis, will be equal to the moment of inertia of the body about the x-axis and about the y-axis. And this is applied only for laminar bodies. So dear student, with this we come to the end of today's lesson. We have learned about moment of inertia and rigid bodies in the last lecture, and today we have learned about some theorems of moment of inertia and their proof. See you in next lecture. Thank you.